Imagine physicists at a conference, sipping stale coffee, when someone drops the phrase, vacuum decay. Suddenly, everyone freezes. Not because it sounds like a household chore gone wrong. Honey, the vacuum decayed, guess we are re-buying a Dyson. But because it has shorthand for reality collapsing like cheap IKEA furniture under a sumo wrestler. This is not your usual doomsday. Black holes? At least you'd see the swirl. Supernovae? Bright fireworks? Free light show? But vacuum decay? It's like the universe installing a software update without telling you. 1 second you're watching Netflix, the next second, nothing. Not even credits. Just deleted files. And here's the kicker. You'd never see it coming. No warning sirens, no Bruce Willis hero arc. One moment you're alive, the next your atoms are politely informed by the cosmos that they no longer exist under current operating terms. That's it. Cosmic blue screen of death. Why do scientists lose sleep over this? Because unlike UFOs or time-traveling lizards in politics, this isn't conspiracy. It's real physics, straight out of quantum field theory. The very framework that explains why particles exist, why forces work, and why your Wi-Fi occasionally hates you. The equations literally whisper, hey, reality might be a temporary lease. Comforting, right? Here's how the nightmare works. Our universe is defined by energy fields. Think of them as invisible wallpaper holding everything together. They're stable-ish, but there's a loophole. What we call vacuum might not be the lowest energy state possible. It could be a false vacuum, the kind of temporary fix you'd use when duct taping a car bumper. Looks fine, drives fine, until, surprise, the bumper falls off on the highway of existence. If the vacuum collapses to a true vacuum, boom. Not the fun kind. A bubble of new physics appears and races across space at nearly light speed, rewriting the rules as it goes. Your atoms? Gone. Your dog? Gone. The Eiffel Tower? Still standing for 0.001 seconds. Then gone. No exceptions. No refunds. Physicists admit this with the same nervous laughter you hear at family reunions when someone brings up politics. Because even though the odds are astronomically low on human timescales, they're not zero, which means that, technically speaking, vacuum decay could already be on its way here. A cosmic wrecking ball traveling invisibly, faster than your internet on payday. And the worst part? If it's coming, you'll never know. There's no detection, no time to prepare, not even a split second to say, well, that escalated. Poof. At this point, you might be wondering, why do we even study this? Why not let ignorance be bliss? Because physicists can't help themselves. If there's a horrifying possibility buried in the math, they're going to dig it up like raccoons in a trash can. And what they found is too fascinating and too terrifying to ignore. So yes, vacuum decay is the single most metal way the universe could end. Forget climate change, asteroids, or rogue AI. Those are appetizers. Vacuum decay is the cosmic main course, the ultimate mic drop, reality itself unplugged. And before you ask, no, this isn't science fiction. This is actual peer-reviewed nightmare fuel. When you hear quantum fluctuations and Higgs field, that's code for the universe might delete itself like a badly written Word document. But don't panic. At least, don't panic yet. Because we've only just started unwrapping this doomsday gift basket, and it's got more ribbons than a Christmas tree. So, if you want to keep peeling back the layers of this cosmic horror show while laughing nervously at the absurdity of existence, make sure to like the video, subscribe, and drop in the comments where you're watching from. Hopefully somewhere cozy, because space itself might not be as reliable as your living room walls suggest. Now, The real question is, what exactly is a vacuum in physics? Spoiler, it's not just nothing. It's worse. Picture this. An intern in a physics lab stares at a supposedly empty box. The professor leans over and says, "Behold, the vacuum." The intern shrugs. Looks like nothing. But the professor smirks, because in physics, nothing is the most crowded nightclub in the universe. Particles are constantly photobombing each other, then vanishing before security kicks them out. See, in quantum mechanics, emptiness isn't empty. It was more like a toddler's bedroom after you. We asked them to clean up. On the surface it looks fine, but under the bed are monsters, crayons, and a leftover peanut butter sandwich from 2019. What you call empty space is actually a seething ocean of energy fluctuations, and those fluctuations never shut up. They keep producing particles that exist for a fraction of a second before disappearing, like failed startups in Silicon Valley. Physicists call this vacuum fluctuations, which sounds calm and meditative until you realize it means that space itself is never stable. Imagine trying to sleep in a room where the bed randomly morphs into a trampoline every half second. That's reality's version of downtime. And this jittery chaos isn't just background noise, it literally defines the structure of existence. Every particle in the universe, electrons, quarks, photons, owes its existence to these restless fields. Without the constant buzz of vacuum energy, there'd be no atoms, no chemistry, no memes about cats. The universe would be flatter than your Wi-Fi after someone starts streaming 4K movies in the other room. So when scientists say, vacuum, don't think empty jar. Think hyperactive casino floor where quantum dice are rolling non-stop. Particles appear, borrow energy from the house, and vanish again before the cosmic accountant notices. And if you're wondering why they're allowed to do that, blame Heisenberg's uncertainty principle. It's the ultimate, "you can't prove I wasn't here" excuse. The particles basically say, "We were never really alive, officer, just visiting." The best part? This background chaos has measurable consequences. The Casimir effect, for example, is when two metal plates placed close together in a vacuum actually pull toward each other. Not because of static, but because the vacuum itself is shoving them. Imagine putting two slices of bread too close together, and suddenly the mayonnaise forces them into a sandwich. That's the vacuum, always making unwanted snacks. And it gets weirder. These fluctuations are what allow stars to shine, black holes to evaporate, and chemistry to keep functioning. Without them, the universe wouldn't just be quiet, it would be boring. Like a party where no one shows up except your aunt, who only wants to talk about her cat's dietary restrictions. But here's the catch. This vacuum we live in might not be the ultimate vacuum. In quantum field theory, the lowest energy state is the true vacuum. What we have could just be a precarious knockoff version. The wish. Calm vacuum. Stable enough to let atoms form, but not guaranteed to stick around forever. Think of it like renting an apartment where the floorboards look fine until you realize they re-supported by duct tape and expired coupons. That's where things get disturbing. If there's a deeper, more stable vacuum lurking beneath ours, then reality is essentially perched on scaffolding that may collapse without warning. Every field that defines the universe, electromagnetic, strong nuclear, weak nuclear, even gravity, could get rewritten overnight if the vacuum decides it's had enough. Which, scientifically speaking, would suck. Literally. To make matters worse, this instability isn't some vague philosophical concern. The Higgs field, the invisible molasses that gives particles mass, is intimately tied to the stability of our vacuum. If that field wobbles too far, the whole stage tips over. Imagine you're at a concert. and the floor suddenly decides it's no longer interested in being a floor. That's what the vacuum might be planning on a universal scale. And before you think, well, if the vacuum is so unstable, why hasn't it collapsed yet? Remember that metastable things can last absurdly long times. Radioactive atoms decay, but uranium can sit around for billions of years before doing anything dramatic. The vacuum might just be biding its time, like a cat staring at a glass of water before knocking it off the table. You know it's going to happen. You just don't know when. Every day you exist inside this humming, buzzing, fake stable vacuum. Your thoughts, your breakfast, your dog's weird bark, all made possible by a cosmic floor that could, in principle, give out. And scientists admit it with a shrug, because the math insists on keeping that option open, which is fine if you enjoy living in a universe that doubles as an existential cliffhanger. But if vacuum is already this unstable carnival of chaos, what happens when physicists whisper about it being a false vacuum? Well, that's when the universe stops being a party and starts being a trapdoor.
Picture the universe as a teenager lounging on a broken beanbag chair. It looks comfortable enough, but one wrong wiggle and the seams explode, launching foam pellets into orbit. That's basically the false vacuum. The idea that our universe only thinks it's in a stable state, but in reality, it's slouching dangerously on cheap furniture from the cosmic bargain bin. Here's the unsettling detail. Energy states in quantum field theory aren't just on or off. They're landscapes. Imagine rolling a marble across a field of hills and valleys. The marble always wants to settle into the lowest valley, the true vacuum, the most stable state. But sometimes it gets stuck in a smaller dip along the way. That's the false vacuum, a metastable pit that looks permanent until the marble finds a crack to slip into the deeper abyss. Now replace that marble with all of existence, and you've got a scenario less cozy than it sounds. Why does this matter? Because if we're in that false valley, then our laws of physics, everything from how atoms hold together to why light moves at 299,792,458 meters per second instead of some awkward number, are propped up by temporary scaffolding. A single nudge, and the constants could reconfigure themselves like a toddler smashing buttons on a TV remote. Gravity might turn off. Electromagnetism might lose interest. Chemistry might decide, bonding is overrated. Physicists describe this potential shift as a phase transition. And no, not like your friend's awkward middle school goth phase. More like water turning to steam. Same molecules, totally different behavior. Only here, the phase in question is the foundation of reality. A false to true vacuum transition would rewrite physics itself, not just break the rules, but shred the rulebook and replace it with hieroglyphics no one can read. The terrifying beauty is in its efficiency. If such a transition ever began, it would start at a single point, like a bubble forming in boiling water. That bubble would contain the true vacuum, the lower energy state, and it would expand outward at nearly the speed of light, converting everything it touched into the new reality. Atoms wouldn't just be rearranged, they'd stop being atoms altogether. Matter, forces, space-time geometry, all swapped out like cheap curtains in a rental apartment. Here's the existential gut punch. You'd never feel it coming. No tremors, no cosmic countdown. One moment, coffee mug in hand, scrolling through memes. The next, your mug, your hand, and the concept of mugs are politely deleted by the advancing bubble wall. Imagine antivirus software running on your computer, except the software decides the computer itself is a virus. Scientists aren't exaggerating when they call this possibility a vacuum catastrophe. Because the false vacuum isn't just a little unstable, it's potentially fatal for reality itself. If we are perched in that metastable dip, then everything we know is hanging by the quantum equivalent of dental floss. It might hold for billions of years, or it might snap before your next grocery run. There's no in-between. And yes, the math backs this up. The equations of quantum field theory suggest that our universe's vacuum energy might not be the absolute minimum possible. If a lower energy state exists, then by definition, the false vacuum is temporary. You can't stop the marble from eventually finding the deeper valley. The only question is how: tunneling, fluctuation, or some random cosmic hiccup. It's like owning a time bomb without knowing if the timer is set for 5 seconds or 5 trillion years. This is why physicists drink. Not because they're all depressed, but because contemplating the fragility of existence goes down easier with whiskey. They study particle masses and field interactions with the same intensity you'd use to check whether your car's brakes actually work. If the numbers tip one way, the universe is stable. Tip another way, and you've been living in an intergalactic waiting room with an eviction notice already printed. And before you think, maybe this is too wild to be true, remember that science has a long tradition of wild things turning out real. Quantum mechanics was once considered nonsense until it started predicting semiconductors and lasers. Black holes sounded like mathematical pranks until telescopes snapped their mugshots. The false vacuum? It's another entry in that list of things too insane to dismiss. So here we are, existing inside a universe that may only be renting its stability, waiting for the landlord, the true vacuum, to arrive and demand renovations. The question gnawing at physicists isn't whether the false vacuum exists, but how close we are to discovering whether the lease runs out tomorrow or in geological time. And the first clue lies in a suspicious little field that underpins the entire show, humming quietly in the background like a fridge you never notice until it breaks. In 2012, physicists at CERN popped champagne because they'd just discovered the Higgs boson. The rest of the world shrugged, called it the God particle, and went back to watching cat videos. But inside the physics community, the mood was more, we just found the manual to the universe, but page 47 casually hints that the manual might self-destruct. Here's why. The Higgs field is the invisible molasses that gives particles mass. Without it, electrons would zip around weightless, protons would act like sugar-free candy, and atoms wouldn't hold together. You wouldn't be here. Your couch wouldn't be here. Even the existential dread you're feeling right now wouldn't be here. All of reality leans on this invisible cosmic glue, like an exhausted college student leaning on a vending machine. The problem? When physicists measured the mass of the Higgs boson, about 125 gigaelectronvolts, which sounds like a lot until you realize it's the kind of number scientists throw around like Monopoly money, they noticed it landed in a very awkward range. Not too light, not too heavy, but suspiciously in between. The kind of in-between that makes theorists nervously mutter about metastability. Think of it like building inspection results for a house. If the Higgs were heavier, the cosmic foundation would be solid, no cracks. If it were lighter, the foundation would crumble immediately, and we wouldn't exist to complain. But at 125 GeV, it's right on the knife's edge. Stable enough for now, but precarious enough that the entire cosmic mansion might eventually collapse into a sinkhole. The universe is basically that one friend who insists, "I'm fine," while sitting under a flickering light bulb and clutching a cracked coffee mug. And it gets worse. The stability of the Higgs field isn't determined in isolation. It's entangled with the mass of the top quark, one of the heaviest fundamental particles. If the Higgs is the Jenga tower, the top quark is the clumsy player yanking out blocks. Measure its mass one way, the tower wobbles but stands. Measure it another, and suddenly you're sweeping splinters off the floor of existence. Every new calculation physicists run seems to reinforce the same unsettling picture. We might be living on the edge of a metastable vacuum. Not firmly doomed, not securely safe, just balanced like a wine glass teetering at the edge of the table during an earthquake. The slightest nudge, and physics could rewrite itself into a new alien rulebook. Why does the Higgs mass matter so much? Because it defines the shape of the vacuum's energy potential. Picture a roller coaster track. The Higgs mass decides how deep the dips are and how stable the hills feel. Right now, we're coasting in a valley that looks safe, but the math suggests there's another, deeper valley hidden beyond a barrier. If quantum tunneling ever lets us slip over that barrier, the ride doesn't stop. It flips into a whole new theme park with entirely different rides, most of which don't allow matter, chemistry, or anything recognizable as life. Scientists like to joke that this is the most depressing lottery ever. A tiny probability of vacuum decay happening right now, multiplied by an infinite timeline where probability eventually wins. If that makes your brain ache, you're in good company. Physicists themselves stare at these numbers like accountants discovering the IRS runs on dice rolls. And yet they keep digging. Because the Higgs is more than just a red flag. It's the key to understanding how fragile our universe might be. The boson isn't just a particle, it's a messenger. Its mass tells us that nature might have engineered a cosmos that looks stable, but is secretly sitting on an invisible trapdoor. That trapdoor isn't a distant philosophical puzzle. It's baked into the equations that let stars shine, galaxies form, and you binge-watch Netflix while eating questionable leftovers. When CERN confirmed the Higgs boson, the world heard discovery. Physicists heard possible expiration date. Imagine celebrating a new car purchase, only to learn it came with tires that occasionally decide to vanish without warning. That's the vibe the Higgs field brings to cosmology. And while the champagne at CERN fizzled out, the unease never did. Because if the Higgs mass really does imply metastability, then the universe is living on borrowed time, propped up by a quantum coin toss. And quantum coins are notorious for landing on their edge just long enough to make everyone sweat. The strange part? Even with this knowledge, no one can say when or if the vacuum might transition. The equations don't give us a countdown clock. They just leave us dangling, staring into a cosmic maybe. Which means the Higgs boson isn't just a discovery. It's a question mark stapled to the heart of physics, pointing straight at the mechanism that could erase reality in less than a blink. And that mechanism has a name that sounds deceptively innocent, like something you'd buy for a science fair, but instead unleashes the eraser of worlds. Imagine the universe as a giant cosmic insurance scam. Everything looks fine. Stars twinkle, planets orbit. You spill coffee on your laptop, but hidden in the fine print is a clause. Warning, may spontaneously self-destruct via bubble of death. That's how vacuum decay operates, not with explosions you can see coming, but with the quiet efficiency of an assassin who doesn't bother knocking. Here's the chain of doom, quantum tunneling. If you've never heard of it, think of particles cheating. Instead of climbing over an energy barrier, they occasionally decide, nah, I'll just phase through. It's like if you got tired of unlocking your front door and simply walked through it because physics decided rules were optional. That same quantum anarchy is what allows the false vacuum to potentially escape into a lower energy state. And when it does, it starts small. A bubble forms, not like champagne at a wedding, more like a soap bubble armed with a cosmic sledgehammer. This isn't a bubble you'd let your kid chase in the backyard. It's a tiny sphere of true vacuum, the deeper, more stable state of existence. Inside that bubble, the laws of physics are rewritten. Outside, everything still looks normal. But the bubble expands. And once it expands, it never stops. The expansion speed? Just shy of light. Which means you wouldn't see it coming, you wouldn't feel a breeze, you wouldn't hear a cosmic pop. One moment your molecules are vibing. The next moment they're informed by the bubble wall that mass and charge are no longer features supported in this reality. It's like software patch notes that delete your operating system mid-sentence. What makes it truly wild is the efficiency. Supernovas take time to burn out. Black holes take eons to evaporate. Vacuum decay skips the foreplay and delivers instant erasure. It's not fire, not implosion, not collapse, it's replacement. Reality as you know it gets overwritten, pixel by pixel, with new physics that may or may not permit atoms. If you're lucky, the new laws allow particles to exist. If not, the bubble expands into a sterile void where existence is an outdated concept. Physicists call this a first-order phase transition, which is a fancy way of saying like boiling water, but meaner. Imagine the universe as a pot of water on the stove. It's calm at first, then suddenly bubbles form and spread until everything's transformed into steam. Only here, the steam doesn't cook your pasta. It erases pasta from the realm of possibility. Goodbye spaghetti, goodbye sauce, goodbye carbon-based life. And because the bubble expands so fast, there's no escape. You can't build a bunker, you can't strap rockets to Mars and flee, you can't upload yourself to a hard drive. The bubble doesn't just destroy matter, it rewrites the rules that let matter exist. If the new vacuum forbids electrons, then not only is your body gone, but the idea of electricity itself is obsolete. It's the existential equivalent of updating to an operating system that doesn't recognize files, folders, or even the concept of on. The scale of it is staggering. The bubble doesn't stop with Earth. It doesn't politely skip the moon or spare Saturn's rings. It consumes everything in its path: galaxies, quasars, black holes. Even the cosmic microwave background, the faint afterglow of the Big Bang, would get wiped away. This is not an apocalypse in the religious sense, where at least a few people get to write memoirs about it. It's total reset, with no one left to complain to customer service. And the kicker? The bubble is indifferent. It doesn't target you. It doesn't care about morality, karma, or how many plastic straws you've used. It's pure physics, blind and efficient. If quantum tunneling decides the false vacuum has overstayed its welcome, the bubble starts, and once it starts, there's no pause button. It's like the world's worst Rube Goldberg machine. Intricate, inevitable, and designed to smash everything at the end. So why does this possibility haunt scientists? Because they can describe it in mathematical detail. The equations show how a metastable vacuum can collapse, how the bubble would nucleate, how it would spread. They can even run simulations of the doom bubble sweeping through space-time. And yet, no calculation can say when or where it might begin. It could be 10 trillion years from now, or it could be happening already, expanding silently across some distant corner of the universe. Which means every moment you live is technically a gamble against cosmic tunneling. Every laugh, every breath, every bad karaoke performance exists only because the bubble hasn't rolled the dice in your neighborhood yet. And what unnerves physicists isn't the unlikelihood, but the fact that it remains possible. If the Higgs field is balanced on a knife's edge, then reality's most spectacular collapse is built into the rules themselves. But the story doesn't end at possibility. Scientists aren't content to shrug at the void and sip coffee. They measure, calculate, and argue about how close we really are to this cosmic knife's edge. And in their debates, one thing becomes clear. The threat of vacuum decay isn't a fantasy invented for sci-fi novels. It's carved into the equations of quantum field theory, lurking with the same unnerving silence as a shadow you only notice when you turn your head. Physicists love numbers the way chefs love salt. They sprinkle them everywhere, sometimes excessively, but without them nothing makes sense. When it comes to vacuum decay, the math isn't just seasoning. It's the entire recipe for how reality might pull a trapdoor routine. And the calculations are unsettling enough to make even seasoned scientists consider a career in accounting. Start with the Higgs potential. Imagine drawing a curve on graph paper that looks like a wobbly wine glass. One dip where our universe currently sits, another deeper dip further out. That graph isn't doodling. It's the map of whether reality is secure or balanced like a drunk tightrope walker. The Higgs mass and the top quark mass are the coordinates, and if those numbers fall in the wrong place, the potential slope leans toward collapse. The math says we're uncomfortably close to that line, like a bowling ball teetering on the gutter. The calculation goes something like this. Plug the Higgs mass, around 125 GeV, and the top quark mass, about 173 GeV, into the renormalization group equations. What you get is a verdict that sounds like a bad medical diagnosis. Your universe appears metastable. Prognosis: indefinite survival, with sudden risk of catastrophic collapse. You don't need a PhD to see why that feels less than comforting. What's wild is that the math predicts probabilities, not certainties. Vacuum decay could be so rare that the expected lifetime of our universe stretches trillions of years into the future. That's the optimistic reading. The pessimistic one? Quantum tunneling doesn't follow your optimism. It's random, blind, and waiting for the right fluctuation. Like a dice game where you don't know how many sides the dice even have, but rolling snake eyes means erase existence. And when physicists say expected lifetime, don't picture an expiration date stamped on the universe like milk in your fridge. It's not best before 2084. It's probability distributions stretched across timescales so absurd your brain gives up. Numbers like 10 to the power of 100 years. That's a 1 followed by 100 zeros. To put it in perspective, the age of the universe right now is a measly 10 to the power of 10 years. We haven't even hit the tutorial level compared to the potential timescale. But even if the odds are astronomically low, the fact that the odds aren't zero is enough to keep scientists awake at 3 a.m., staring at ceiling tiles and questioning their career choices. And if you think these calculations sound suspiciously like doomsday prophecies, you're right, but with actual math instead of vague threats about blood moons. For example, theorists like Sidney Coleman worked out how quantum tunneling could trigger vacuum decay back in the 1970s. They described how the false vacuum might decay into bubbles of true vacuum, expanding faster than light. The math was elegant, terrifying, and published with the same casual tone as a recipe for banana bread. That's academia for you, calmly announcing the death of everything between conference coffee breaks. Even the energy scales involved are monstrous. The potential difference between the false vacuum and the true vacuum is thought to dwarf anything we can produce in a lab. The Large Hadron Collider smashing protons together at 13 TeV? Child's play compared to the energy gap needed to trigger vacuum decay. That's comforting until you remember nature doesn't need permission. Cosmic rays hit Earth's atmosphere with energies millions of times greater than anything humans can produce. And so far we've been lucky. Lucky in physics is never a long-term strategy. Some argue the universe's very survival after billions of years suggests we're safer than the math implies. But probability doesn't care about your feelings. Russian roulette can go 5 empty clicks before the bullet fires, and you'll still regret every pull of the trigger. In physics terms, surviving this long might just mean the dice haven't landed against us. Yet. The kicker is that these equations don't just sit on paper. They're tied to experiments. Every time physicists refine the measurement of the top quark's mass, the stability calculation shifts. A fraction of a GeV one way, and we're stable. A fraction the other, and we're doomed. It's like learning your life expectancy depends on whether your bathroom scale rounds up or down. And here's the part that makes physicists sweat through their lab coats. The current best measurements put us in the metastable region. Not solid ground, not immediate collapse, just perched awkwardly between stability and doom. The cosmic equivalent of standing in an elevator that might work fine or might plummet at random. You ride it anyway because, well, where else are you going to go? So the math is clear, the equations are merciless, and the numbers point toward a reality where vacuum decay is baked into the menu. But math alone doesn't kill universes. Something has to trigger the fall, and nature has a way of providing plenty of candidates that look suspiciously like loose matches around a room full of dynamite. If vacuum decay is a gun pointed at the universe, the obvious question is, what could pull the trigger? Spoiler, nature has a long list of suspects, and none of them look guilty until you squint at the math. The first candidate is high-energy particle collisions. When physicists fired up the Large Hadron Collider, tabloids screamed scientists could destroy the universe. Physicists, exasperated, explained that cosmic rays slam into Earth's atmosphere with far more energy than anything man-made. Translation: if smashing particles could pop the vacuum like a cheap balloon, the cosmos would have already been cancelled. Still, the anxiety wasn't entirely misplaced. Those collisions do test the very conditions that define stability, which is why every time the LHC powers up, theorists look like people about to press a suspiciously large red button. But cosmic rays themselves are far scarier. These particles streak through the universe with energies so absurd they make human experiments look like toddlers throwing Cheerios. When they slam into atoms in our atmosphere, the impact dwarfs anything we've engineered. Each one is a test run of reality's foundations, a natural stress test we never signed up for. That we're still here after billions of years suggests resilience, or that we're running a marathon on ice, and the cracks just haven't reached us yet. Then there are black holes, those cosmic garbage disposals that eat everything unlucky enough to stray too close. In quantum field theory, black holes aren't just vacuum cleaners, they're laboratories of extreme physics. At their event horizons, energy densities soar, space-time bends, and quantum effects go feral. Some theorists worry these conditions could nudge the vacuum into instability, the way shaking a soda can make it erupt. Hawking radiation, the quantum leakage from black holes, only adds fuel to the paranoia. When the universe's most mysterious objects are belching particles into the void, it's hard not to wonder if they're also rolling dice on reality's stability. And let's not forget phase transitions from the early universe. When the cosmos was young and hotter than your microwave pizza, it went through rapid transformations. Inflation ending, forces splitting apart, particles gaining mass. Each step was a high-energy upheaval, like a toddler redecorating a living room with crayons. Those transitions didn't trigger vacuum decay. Lucky us, but they remind physicists how fragile the system can be. The fear is that another transition could be hiding in our cosmic future, waiting to destabilize the vacuum again. Even dark energy, that mysterious force accelerating the universe's expansion, raises suspicions. Nobody knows what it really is, a field, a constant, a cosmic practical joke. But its behavior shapes the fate of spacetime. If its properties shift, even slightly, it could alter the balance of the vacuum. Imagine baking a cake and having the oven randomly change temperature mid-recipe. Only here, the cake is existence itself, and the oven doesn't beep when things go wrong. The unsettling part is that none of these triggers need our permission. They're woven into the fabric of the cosmos. We can't switch off cosmic rays, stop black holes from spinning, or renegotiate with dark energy. Physics is playing Jenga on a cosmic scale, and every natural process is another hand tugging at the tower. But humans being humans, we've tried to make it worse. Our experiments at higher and higher energies may not match cosmic rays, but they still poke at the boundaries. Every collider test is another question whispered into the void. Hey, universe, are you really stable? It's like tapping the glass of an aquarium filled with sharks. You probably won't crack it, but if you did, it wouldn't end well. Physicists debate which trigger is most likely, but the depressing answer is that we can't know. The equations allow for multiple routes into vacuum decay, and the universe isn't in the habit of sending warning memos. One day, a fluctuation somewhere in the void could nucleate a bubble, and from there the story writes itself in erasure ink. The irony is that this fragility doesn't paralyze science. It motivates it. The more we learn about high-energy physics, black holes, and cosmic rays, the more we're forced to confront the possibility that reality's stability isn't guaranteed. And with every new measurement, the picture sharpens into something both terrifying and fascinating. A universe that survives not because it's indestructible, but because chance has spared it so far. Which leaves physicists staring at the triggers like detectives at a crime scene. Knowing the weapon is loaded, the suspect list is endless, and the victim is everything that's ever existed. And the only way to move forward is to dig deeper into the one place that might hold an answer. The very structure of spacetime itself, where the seeds of instability are already whispering. Spacetime isn't the smooth, elegant fabric you see in pop science documentaries where apples roll on rubber sheets. It's more like a lumpy air mattress at a sketchy motel. Uneven, noisy, and full of mysterious leaks you don't want to think too hard about. Quantum mechanics insists it's constantly buzzing with fluctuations, like static on an old TV. General relativity insists it should bend gracefully under mass and energy. Combine the two, and you don't get harmony. You get a screaming match that threatens to destabilize everything. At small scales, spacetime is chaotic. Virtual particles blink in and out, fields jitter, and the very metric that defines distance and time jitters like a caffeinated squirrel. This constant agitation isn't decorative. It feeds directly into vacuum energy. And if you tally up the numbers, quantum field theory predicts a vacuum energy density so enormous it would curl the universe into a microscopic ball faster than you could say oops. Yet the real, observed vacuum energy is tiny. It's the most embarrassing mismatch in physics, off by about 120 orders of magnitude. That's not a rounding error. That's asking your GPS for directions to Paris and being told to swim to the moon. This mismatch is called the cosmological constant problem, and it gnaws at every attempt to reconcile quantum mechanics with relativity. On one hand, the equations scream instability. On the other, the universe clearly hasn't folded in on itself. It's like your doctor telling you your blood pressure is so high you should be dead, while you're sitting there munching chips. Something in the math doesn't add up, but the threat lurking in the numbers refuses to vanish. Then comes gravity. Unlike the other forces, gravity doesn't politely fit into the framework of quantum field theory. It crashes the party like an uninvited uncle, messing with the furniture. At extreme densities, say inside black holes or during the first instant after the Big Bang, gravity warps spacetime so violently that the usual rules collapse. And when rules collapse, vacuum stability is anyone's guess. Maybe space-time foam smooths itself out. Maybe it tears open pathways that let the vacuum tunnel more easily. The uncertainty keeps theorists awake like kids convinced there's a monster under the bed. Inflation theory adds more unease. According to it, the early universe expanded faster than light, driven by a high-energy field that eventually decayed into the vacuum we inhabit today. But if inflation could happen once, what stops runaway patches of space-time from inflating again? Eternal inflation suggests the cosmos is a bubbling foam of universes, each pocket with its own vacuum state. Ours just happens to be balanced precariously. Others might already be gone, devoured by vacuum bubbles that erase their physical laws before they had a chance to brag about inventing fire. And while physicists wrestle with equations, space-time itself offers no reassurance. Every gravitational wave detected by LIGO is a reminder that space-time isn't static wallpaper. It ripples, stretches, and flexes. Those waves are born from catastrophic collisions of black holes and neutron stars, where densities spike to absurd levels. In the chaos of those events, vacuum fluctuations aren't just background noise, they're players. When space-time bends that violently, who's to say it doesn't occasionally push the false vacuum over the edge? The terrifying elegance is that space-time doesn't need a catastrophic event to betray us. Quantum tunneling means the vacuum can collapse spontaneously, even in the most boring corner of the cosmos. But the presence of curvature, waves, and energy density might amplify that chance. It's like living in a house that could collapse at random, but knowing earthquakes, windstorms, and clumsy elephants walking nearby all make the odds worse. The house might stand for ages, or it might decide the next sneeze is too much. The attempt to merge quantum mechanics with general relativity, the fabled theory of quantum gravity, is supposed to answer whether spacetime is strong enough to hold our vacuum in place. String theory, loop quantum gravity, holographic principles, all grand contenders. Yet each offers a different verdict on stability. Some argue our vacuum is metastable but long-lived. Others claim hidden dimensions could destabilize it. It's the physics equivalent of getting 5 doctors' opinions and discovering they can't agree on whether you need surgery, medication, or a ritual involving goats. What makes it worse is the sheer indifference of the numbers. No matter how you bend the equations, space-time seems determined to remind us that our universe rests on a razor's edge. And the more precisely we measure particle properties and cosmic expansion, the sharper that edge becomes. Physicists peer into their blackboards and see not just curved geometry, but the outlines of a ticking mechanism we barely understand. So space-time isn't a serene backdrop. It's an active participant, jittering, flexing, and stretching in ways that may carry the seeds of collapse. And when every ripple, fluctuation, or cosmic collision might be tugging at the thread of vacuum stability, the question isn't whether the fabric will ever tear. It's how tightly we're actually clinging to it while the edges fray. Tell someone the universe might collapse into a bubble of doom at light speed, and you'd expect screams, riots, or at least a strongly worded letter to the cosmos. Instead, the usual reaction is a shrug followed by, "Cool, so what's for lunch?" Humans are notoriously bad at processing risks that don't come with flashing lights or car insurance commercials. Psychologists would call this optimism bias. The brain is wired to believe catastrophe always happens to someone else. We buy lottery tickets thinking the odds are in our favor but dismiss vacuum decay because the odds are too small. Both are astronomically unlikely, but one comes with scratch-off cards at the gas station. So our lizard brains decide it's worth caring about. Even when people do take it seriously, their solutions are unintentionally hilarious. Some propose building early warning systems to detect a bubble of true vacuum. Great idea, except the bubble expands at light speed, which means by the time you detect it, congratulations, you've already been deleted. That's like inventing a fire alarm that only goes off once the house has already burned to ash. Others suggest we might one day escape by traveling to another universe. Sure, just invent interdimensional travel. Figure out how to survive physics constants that don't allow atoms, and also do it before the bubble reaches your neighborhood. It's the same energy as telling a drowning man he should just build a boat. Governments don't help either. Politicians can barely agree on potholes, let alone vacuum decay. Imagine a Senate hearing where someone proposes funding Project Don't Let Reality Erase Itself. The budget office would laugh them out of the room faster than you can say Appropriations Committee. Even if the math is bulletproof, the threat lacks the one ingredient politicians love: voters who care. No votes, no money, no defense plan. Physicists, on the other hand, live in a perpetual cocktail of fascination and existential dread. They publish papers calmly detailing how existence could end with the detachment of someone writing IKEA instructions. To the outsider, this looks psychotic. To the physicist, it's Tuesday. They cope with the horror by turning it into conferences, equations, and the occasional dark joke. Imagine a workplace where gallows humor isn't just tolerated, it's peer-reviewed. And society at large? It finds ways to meme it. Vacuum decay becomes a trending hashtag, slapped on images of cats staring into the void or SpongeBob dissolving into nothingness. Somehow, turning cosmic annihilation into shareable content makes it less scary. If you can caption it with impact font, it can't hurt you. Except it literally could, without warning, which only makes the memes funnier. But buried under the memes and shrugs is a real psychological trick. Humans handle abstract terror by trivializing it. We can't fight quantum tunneling, so we mock it the same way people laugh nervously at horror movies. Laughter is anesthesia for the species. If you can joke about vacuum decay, you've bought yourself 5 minutes of sanity. Yet every so often, the weight of it cuts through. Imagine lying awake at night realizing everything. The books on your shelf, your favorite sandwich, the memory of your grandmother's perfume exists only because the Higgs field hasn't slipped. The thought doesn't spark panic attacks in most people because the brain politely files it in the too much, do not open drawer. But for those who do let it in, it's the purest form of existential vertigo, knowing the cliff exists but never seeing how far down it goes. And here's the kicker: that vertigo fuels curiosity. The very fact that existence hangs by a quantum thread makes people ask bigger questions. Why is there something instead of nothing? How fragile is the framework holding atoms together? What kind of universe could exist if this one rewrote itself midstream? Questions that sound poetic over coffee are backed by equations grim enough to haunt graduate students. So humanity wobbles between denial, jokes, and awe. We ignore the threat because it's abstract, we laugh at it because it's absurd, and we study it because not knowing is worse. But even as the collective reaction tilts toward apathy, the fact remains that every breath we take is borrowed time from a vacuum that hasn't betrayed us yet. And the real question isn't how we react now, but what happens when we discover evidence that our lease on existence is shorter than we thought. The universe has a terrible habit of leaving breadcrumbs that point to its fragility, and physicists, being gluttons for punishment, can't resist following them. One of the juiciest crumbs comes from precision measurements of the top quark. This isn't just any particle. It's the diva of the Standard Model, heavier than an entire gold atom and so unstable it decays before anyone can take a flattering photo. And the exact mass of this prima donna is the number that decides whether the Higgs field locks reality into stability or leaves it teetering like a folding chair with one leg shorter than the others. Measurements so far put the top quark's mass in the danger zone. Not run for your life danger, but the universe might be metastable danger. A polite way of saying our existence could be a cosmic rental agreement. Physicists refine this number obsessively, because nudging it by even a fraction of a GeV shifts the whole verdict. That's like finding out whether your house is built on bedrock or quicksand depends on whether the contractor's tape measure was off by a millimeter. Then there's the Higgs boson itself. When CERN discovered it in 2012, headlines called it the God particle, a branding choice that made scientists want to crawl under their desks. The real story is less divine and more like opening a fortune cookie that reads, "Congrats, your universe might not last." The Higgs mass sits in an awkward range that practically screams metastability. It's as if nature deliberately chose the one number that maximizes existential dread, just to see how we'd handle it. Spoiler, with memes and conference papers. Cosmology adds more unease. The discovery of dark energy, that mysterious push accelerating the expansion of the universe, implies the vacuum isn't just sitting still. It has energy, and that energy is stretching spacetime like taffy. The problem is that dark energy behaves like a cosmological constant, the very quantity quantum field theory bungled by 120 orders of magnitude. Imagine hiring an accountant who misses your tax bill by a factor of a trillion. You'd fire them instantly, but in physics, you just keep using the equations and hope reality doesn't notice. The cosmic microwave background also whispers clues. Tiny fluctuations in that afterglow from the Big Bang show how matter clumped to form galaxies. But they also hint at the fingerprints of inflation. If inflation theory is correct, our vacuum is just one bubble among many in a larger frothy multiverse. And bubbles in a multiverse don't all share the same stability. Somewhere out there, another universe might have already popped, leaving nothing behind but expanding oblivion. Ours hasn't, yet, but the evidence that universes can differ at all suggests our stability isn't a guarantee. Astrophysics doesn't get kinder. Neutron stars, those ultradense stellar corpses, compress matter so intensely that protons and electrons merge into neutrons. They're basically cosmic pressure cookers where quantum chromodynamics plays Jenga with the laws of matter. Theorists speculate that under those insane conditions, exotic phases of matter could form. Phases that flirt dangerously close to what a true vacuum might look like. If one of those stars were unstable enough, it could theoretically seed collapse. That hasn't happened, or we wouldn't be talking, but the fact that it's even in the equations is like seeing possible fatal side effects on the medication you already swallowed. Even the stability of fundamental constants looks suspicious. The fine structure constant, which governs how strongly particles interact with light, seems immutably fixed. But experiments check its value across billions of light years by analyzing distant quasars, and the tiniest hint of variation makes everyone sweat. If constants can drift, so can the conditions that keep our vacuum perched where it is. A shift in the wrong direction isn't just inconvenient. It rewrites the laws that let atoms exist. All this evidence stacks into a picture where our universe looks less like a fortress and more like a precarious campsite in a storm. The fire's still burning. The tent hasn't collapsed, but the wind is howling and the stakes look wobbly. Physics papers don't phrase it like that. They prefer dry graphs with shaded regions labeled stable, metastable, and doomed. But the translation is clear. We're squatting in a reality that doesn't inspire confidence. And what makes the evidence so unnerving is how consistent it is. Independent measurements of the Higgs, the top quark, cosmic expansion, and the microwave background all point toward the same unsettling conclusion. We're balanced on a knife edge. It's like hearing 5 different mechanics tell you your car might explode, but none can agree when. You can still drive it, but every traffic light feels like a dare. The universe, it seems, isn't shy about dropping hints that it's temporary. Each experiment is another nudge toward the realization that stability isn't the natural state. Precariousness is. And the more data we collect, the less it looks like we're living in a perfectly tuned cosmos, and the more it looks like we're clinging to a cosmic compromise that could, under the right fluctuation, snap without warning.